Hello, welcome to today's class. We'll start with the very first unit number 1, interference and diffraction. We'll start with the interference phenomena. Here we will see the very two specific experiments, that is Newton's rings and Michelson's interferometer. And here we discuss Newton's rings experiment along with its theory. So we already studied the phenomena of interference and we explained it by using wave theory of light. And again we deal with the interference formed in thin films. Interference in thin films due to reflected light and interference in thin films due to transmitted light. Newton's rings is particular example of an interference formed in thin films, where thin film is of air and it is formed by putting curved surface of a plano-convex lens over a plain glass plate, as shown in a figure on this slide. It is observed that the thin film has a varying thickness. The thickness of the thin film increases from point of contact gradually towards outside. The thickness is very small near the point of contact and it gradually increases from center or from point of contact to outwards. So this is a thin film used by Newton to observe the interference in it. Now how he observed the interference in this thin film? Let us see. The fringes produced by using the monochromatic light. So the thin film is illuminated with a monochromatic light like sodium light, and fringes are observed. It is observed that fringes are concentric circular fringes which are alternate dark and bright fringes. These are alternate bright and dark concentric circles. Fringes are concentric circles which are alternate bright and dark with the monochromatic light like sodium light. But when the white light source is used, the fringes are again concentric circles, but these are colored fringes, since white light has 7 different colors from red to violet. So this is about the fringes. And since fringes are in the form of rings, these are famous, the fringes are famous by the name that Newton's rings. And accordingly the experiment is called as Newton's rings experiment. Now how this experimental setup is and how it works, let's see. The experimental setup of Newton's rings experiment is shown in the figure on this slide, where S is a monochromatic source of light which is kept at the focus of the lens L1. The light coming from monochromatic source is made parallel by the lens L1 and it is incident upon a glass plate B. The glass plate B is inclined to horizontal axis at an angle of 45 degree. Parallel rays of light incident upon glass plate B reflect. The part of light is reflect towards the air film produced by lens L and glass plate G. The light rays are again reflected back from the lower surface of the lens and upper surface of the glass plate, and the interference is produced between these reflected rays within the air film. The interference produced in the air film is observed by using a microscope M shown on the upper side of the figure. So this is about the experimental setup. Now how the radius of the rings is measured, that we will see in the next slide. Now let us see how the radius of the rings is measured, that is theory. And here as a first case we will consider the Newton's rings produced by reflected light. Now again here look at the figure, very first one, where lens L is kept over a glass plate, plain glass plate G, and the air film is formed. The light is incident upon the air film and you will observe that it gets reflected from lower surface or curved surface of the lens, and then part of the light get reflected from upper surface of the glass plate, and interference between these two reflected rays is supposed to be produced, which gives rise to rings pattern. Now consider that capital R is radius of curvature of the plano-convex lens, and small t is thickness of the air film at a distance small r. Now look at the figure, second figure here, towards right hand side of this slide. T is thickness of the air film at a distance r from the point of contact O, that means at point Q. The thickness is supposed to be r, thickness of the film is supposed to be r, as we have seen that the thickness T is thickness at a distance r, so OQ is equal to r. So thickness is gradually increasing from point O towards outside. So at point Q, at a distance r from point of contact, the thickness is T at a distance small r. Okay. Now interference pattern consists of concentric alternate bright and dark rings, bright and dark circles. So here we are considering interference due to reflected light. Let us consider a bright ring. According to theory of interference produced in thin film by reflected light, the formula for bright interference fringe is 2 mu t cos theta equal to 2n minus 1 lambda by 2, where n is an integer which can take values 1, 2, 3, etc. Let us call this as equation 1. Now in the present case, the theta is very small. Theta, the angle of refraction is very small, so near to 0, therefore cos theta is equal to 1. And again, film is air film, therefore mu is equal to 1. Refractive index of air is 1. So by putting these two values, we find that formula 1 reduces to 2t equal to 2n minus 1 into lambda by 2. Okay, so this is about the bright rings. Now for dark rings, again we are using the formula for dark fringe according to theory of interference in thin films due to reflected light, and the formula for dark fringes is 2 mu t cos theta equal to n lambda. Again, mu is equal to 1 for air and cos theta equal to 1 for theta to be very small, so therefore this formula reduces to 2t equal to n lambda, where n can take values from 0, 1, 2, etc., etc. Let us call it as equation number 3. Now look at the geometry of the figure towards right hand side of the slide. From the geometry of figure, we can have the formula shown here, that is distance EP multiplied by distance HE, so distance towards both sides of the point of contact, equal to OE into 2 into capital R, where capital R is radius of curvature of the lens, minus OE is again thickness. So by putting EP equal to HE equal to small r, the distance at which thickness is T, and by putting OE equal to PQ equal to T, we find that, and again by using that analogy that 2r minus T, where 2r is in meters, okay, and T is in fraction of millimeter, so 2r minus T can merely substituted as 2r. So the formula will be r square equal to 2 into capital R into small t, so T thickness is equal to r square upon 2r, small r square upon 2 into capital R. So this we have solved by the geometry of the figure here. Now putting value of T in equation 2 and 3, that is equation for bright ring and dark ring, we find that for bright rings, so the equation here we have substituted T equal to r square upon 2r, so that equation reduces to r square equal to 2n minus 1 lambda r upon 2. Let us call it as equation number 4. What is r? It will be square root of 2n minus 1 lambda r upon 2. Let us call it as equation 5. This gives you radius of the bright ring. And what about for dark ring? Using equation, putting thickness, putting the value of small t in equation 3, it will be 2 into r square upon 2r equal to n lambda, and r square equal to n lambda r. Let us call it as equation 6. Therefore r equal to square root of n lambda r, it is radius of the dark ring. So in this way, equation 5 and equation 6 gives us radius of bright ring and radius of dark ring. Now concentrate upon equation 6, that is radius of dark ring. If we put n equal to 0, the radius of dark ring is found to be 0. And what about radius of bright ring? It is equal to square root of lambda r upon 2 according to equation 5. So radius of dark ring for n equal to 0 is 0. So we have to measure from any when equal to 1, 2, 3 as dark ring 1, dark ring 2, dark ring 3. For n equal to 0, radius of dark ring is 0, means center is a dark patch. Center is not a dark ring as shown in the figure, and alternate bright and dark rings are produced. So remember that in case of Newton's rings due to reflected light, center is a dark spot or dark patch, and alternate bright and dark rings are produced for reflected light. Now, if we are looking at the formula, we will find that radius of dark ring is proportional to 3 different parameters. That is directly proportional to square root of n, directly proportional to square root of lambda wavelength, and directly proportional to square root of capital R, the radius of curvature of the plano-convex lens. Again, for bright ring, we will find that radius of the bright ring is directly proportional to the factor square root of 2n minus 1 upon 2, where n is order of the ring. Then directly proportional to square root of lambda, wavelength of light used, and square root of capital R, the radius of curvature of the plano-convex lens. So it is observed that more the wavelength, more will be the radius of the rings. And again, important to note that more flat is the plano-convex lens. That means more will be the radius of curvature of the plano-convex lens, the more will be the radius of the rings produced in the interference pattern. Now, let us find one important fact. Now look at the diameter of the dark ring. Radius is square root of n lambda r, so diameter it will be equal to double the radius, that is 2 into square root of n lambda r. So for n equal to 0, diameter is 0. So the center of this is the center of the Newton's rings pattern. We call it as a dark spot, not a ring. So at the center of the Newton's ring pattern, due to reflected light, there is a dark spot. Now, order of the ring thus can be counted like dark ring can be counted like as n equal to 1, 2, 3, where n equal to 0 is not counted. So this is clear, because at 0 there is no ring, there is a spot. Now for the first dark ring, for n equal to 1, diameter it is equal to 2 into square root of lambda r. For the second dark ring, n equal to 2, and diameter is equal to d2, say equal to 2 under root 2 lambda. For nth dark ring, the diameter is dn equal to 2 under root n lambda r. Now consider the very specific two dark rings, that is 16th and 9th dark ring, just for our convenience to find the square roots. So d16, so diameter of the 16th ring is equal to 2 square root of 16 lambda r. Square root of 16 is 4, so it is 8 square root of lambda r. And diameter of 9th dark ring, that is d9, equal to 2 under root of 9 lambda r. So it is equal to root of 9 is 3, so it is equal to 6 under root lambda r. Now what will be difference of diameters between this 9th and 16th dark ring? So d16 minus d9 equal to 8 under root lambda r minus 6 under root lambda r. This is equal to 2 under root lambda r. Similarly, difference between 4 and first dark rings, difference between diameters of 4 and first dark rings, that will be equal to d4 minus d1, and that is equal to 2 under root 4 lambda r minus 2 lambda r. So that will be equal to 4 under root lambda r minus 2 under root lambda r, again 2 under root lambda r. What you will find here? From this, it is observed that from 16 to 9th order, from 16 to 9th order, there will be 7 rings and their thickness is equal to 2, their difference, or they are accommodated in the range, that is 2 under, in the thickness 2 under root lambda r. And from first to fourth ring, only 3 rings are there. They are again accommodated in the same space. It clearly means that when the order of the ring is increased, so fringe width decreases. The width of the ring decreases and fringes get closer together. Same you can observe on the interference pattern for reflected light shown in this figure, that fringe width decreases with the order. So initially at the near the center, the width of the fringe is large and width reduces gradually when we go outside. In other words, fringes get closer and closer with the increasing order. So fringe width decreases with the order of the fringe and fringes get closer with the increasing order. This is the important fact we observe in the interference fringes of Newton's rings pattern. So this was about the theoretical details. So important to remember here that the radius of the rings depends upon 3 different factors, that is order of the ring, more the order, more will be the diameter, wavelength of the light used, more the wavelength, more will be the diameter and radius of curvature of the plano convex lens, more will be the radius of curvature, bigger rings will be produced. Now look at the theory of transmitted light. Now how interference in the thin film is produced, that is shown in the first figure. You will find that from the lower surface of the convex lens, the ray is reflected and get transmitted, and the one ray is get transmitted from the upper surface of the glass plate, and interference is produced in this way between the transmitted light. Now the interference fringes are produced in such a way that, again, now here we have to use the theory of interference in thin films due to transmitted light, and according to that theory, the condition for bright fringes is 2 mu t cos theta equal to n lambda. So it is different than the rings pattern due to transmitted light, reflected light. Okay, there it may be the formula for dark ring, here it is for bright ring, 2 mu t cos theta equal to n lambda, and for dark rings it is equal to 2 mu t cos theta equal to 2n minus 1 lambda by 2. Exactly alternate formulas are there. Okay, so in case of reflected light, which was for bright ring, here the formula for dark ring, and which was for dark ring, here the formula for bright. So remember very well. Again we have to use that analogy that theta is very small, so therefore cos theta equal to 1, and since the film is air film, so mu equal to 1. So for bright rings, here for transmitted light we have 2t equal to n lambda, and for dark rings here 2t equal to 2n minus 1 lambda by 2. Again from the geometry of the figure, that is the geometry of the thin film, you will find that small t, thickness at a distance small r, is equal to t equal to r square upon 2 into capital R, where small r is radius of the ring and capital R is radius of curvature of the lens. Okay, radius of the ring, small r is radius of the ring, at where the thickness of the film is small t, and capital R is radius of curvature of the lens. So by putting this value, we find that radius of bright ring for transmitted light is equal to square root of n lambda r, and that of the dark ring is equal to square root of 2n minus 1 lambda r upon 2. Again, exactly the alternate equations. There, radius of, in case of reflected light, radius of the dark ring is square root of n lambda r. Here, in case of transmitted light, it is the bright radius of bright ring. Okay, and again, so it is alternate thing. Remember very well. Now, if n equal to 0 for a bright ring, we will observe here that radius r is 0. That means here for bright ring the radius is 0, so center is a bright spot, not a bright ring. Okay, and it is just opposite to what we have observed in case of reflected light, where the center is dark spot, not a ring. Okay, so here it is bright spot, opposite to the pattern of the reflected light. So you can observe here. Again, you will find one important thing is that the thickness or width of the fringes is large at the center, near the center, and it reduces gradually from center to the outwards, and the fringes get closer and closer with the increasing order. It is the same result which we have observed in case of interference pattern due to reflected light. So it was about the theory and experiment of the Newton's rings. Let us see one important application of the Newton's rings experiment, that is determination of wavelength of sodium light. Now, experimental setup is one and same. Here again we are using monochromatic source of light. So lens L1 make the rays parallel, and the parallel rays are incident upon plate B, glass plate B, which is kept at an angle of 45 degree with the horizontal axis. Okay, the rays from plate B gets reflected and incident upon the air film from which they gets reflected, and interference produced between the rays reflected from lower surface of the lens and upper surface of the glass plate, and this interference is observed by a microscope M kept on the upper side of the figure. Now, microscope is a traveling microscope, so we can vary the distance according to our requirement. So the interference fringes will be as shown in the lower figure. Now consider any dark ring and measure its diameter. Suppose we have considered nth dark ring, maybe second, third, fourth, first, ninth, 10th, whatever it may be. Let us call it as nth dark ring, dn. Its diameter will be 2 into square root of n lambda r, and square of the diameter will be 4 into n into lambda r. Let us call it as equation 1. And now measure the diameter of n plus mth dark ring, and it will be say dn plus m, and it will be equal to 4 in the bracket n plus m lambda r. In place of n, now it will be n plus m. Now subtracting equation 1 from equation 2, we find that dn plus m square minus dn square equal to 4m lambda r. It is quite clear. We can rearrange the formula for measurement of wavelength. So lambda equal to dn plus m square minus dn square, that is diameter of n plus square of diameter of n plus mth ring minus square of diameter of nth dark ring divided by 4 into m into r, where m is difference between orders of the ring. And by using this formula, we can calculate the wavelength lambda. Okay, where diameters we are directly measuring, order difference between the orders. Again, it depends which rings we are considering, which we can observe directly. And R, capital R, is radius of the plano convex lens, that can be measured by using the instrument's thermometer, and more accurately it can be measured by using Poisson method. If we are considering the 15th dark ring and 5th dark ring, diameter of 15th dark ring, if we measure diameter of 15th dark ring and 5th dark ring, then what will be formula? It will be d15 square minus d5 square divided by what is m? 15 minus 5 equal to 10. So 4 into 10 into, and in this way we can calculate, we can determine the wavelength of the sodium light. Now this is the last slide. For comparison, we have shown the interference fringes, that is Newton's rings for reflected light and transmitted light. So you will find that the important difference is that which portion, the portion which was bright in the reflected light, interference pattern of Newton's rings of reflected light, is now dark in the transmitted light. So one is negative of other, or other is positive of previous. Okay, so it is like this. Whatever you will observe black in the reflected light, it is observed white in the transmitted light. Thank you for your concentration. Thank you for your patience. Thank you for listening carefully. Thank you very much.